Today we're going to talk about regulated mods. And this is an extension of my video on unregulated mods. And I'll give you the link so you can check that out. So some things I'm not going to talk about too much in this video are system resistance, like the wire resistance and the resistance of the connections and the internal resistance of the batteries. I'll make mention to them, but if you want to understand them better, you should go check out my other video. So what makes a regulated mod? And what makes it different from an unregulated mod? Well, let's start adding components. I'm going to represent the regulator today as this object, as this shape. And I'm not going to go into any more detail about it than that. Later on, I'll link you some videos where you can delve much deeper into it. But this is more for the end user, and maybe some clarification for some novice modders who are making their own boxes. So instead of having a simple switch, like we had in the unregulated mod, we add a regulator and another connection. At a minimum, we have 3 wires connected to the regulator. Positive voltage in, negative voltage in, or ground, as a lot of regulators call it, and positive voltage output. And this is because the regulator switches the positive side. There are regulators that switch both sides, and they're called isolated. We're not going to talk about them today. So we have a negative wire and a positive wire that go and provide power to the regulator. And what comes out is the regulated voltage that goes to the atomizer. And so we have an uninterrupted negative bus, which means all of our negative wires come together at some point, whether it's feeding to the output or to the input of the regulator. And we have an interrupted positive right here. So we have one voltage that comes into the regulator and a different voltage that comes out. And we can have several voltages that go into the regulator. These are just examples of lithium-ion battery voltages that you might see. So we have to add an output adjustment to the regulator so that we can adjust it. And we have to have a fire switch so we can actually fire it. That should make pretty good sense. And that's what makes our generic regulated mod. In the most general sense, this is all you need for a regulated mod. To get a little more specific, when we talk about output adjustment, we're talking about a potentiometer actuator. And the potentiometer is nothing more than a variable resistor. And if you're not sure what that is either, just ignore that. We're going to talk about what an actuator is, which is a knob or a thumb wheel or something that allows you to turn a device that changes the voltage output. Or you can have switch buttons. You push one button for up, another button for down. It's that easy. And the fire switch doesn't have to be an extension of the regulator. Often it is, where the regulator has a on-off control that you actuate using a fire switch. However, if it doesn't, or if you wish to do it differently, you can interrupt the load current right here. Now the implication of that is that all the current drawn by your atomizer has to go through your switch, whereas before, none of your current drawn by the atomizer goes to the switch. The only current that you have to deal with is maybe a couple milliamps, and that's nothing. With a couple of milliamps, you can run your fire switch on Canthal, and it'd be fine. However, in this case, you have to use whatever gauge wire is required by your system, whether it's 18 gauge, 20 gauge, or even 14 gauge. And that's pretty large wire. Another way you can mount your fire switch is to put it on the input instead of where it was before, on the output. When it's on the input, you disconnect the regulator completely. And the advantage to that is the regulator does draw power even when it's not firing the mod. It may only be a few milliamps, but it'll drain your batteries over time. So this is one advantage to this setup. And there are other ways that people do this. They'll put a master switch here, and then they'll have the fire switch here still. That's a little beyond the scope of the video. So we have 3 types of regulators. We have a buck, which is a step down, and that means that whatever voltage you put into the regulator, what comes out is less. You have a boost, which is a step up, and along those lines, whatever voltage you put into it, more comes out. And a buck boost, which can do both. And that's the last time I'll talk about buck boost in this video. So going back to our generic regulated mod, I want to clean up the screen a little bit and talk about power in and out. And this is the most important concept I'm going to convey to you in this video. If you don't get anything else out of it, I hope that you focus on this. So we know we start out with a certain number of watts that the battery supplies. And in an unregulated mod, watts in at the battery is roughly going to equal watts out, what's at the atomizer, minus any efficiency losses. However, in a regulator, we have an added component that we have to deal with, and that's watts lost. Now that's 5 to 15% roughly of your system. And some systems are more efficient than 5% loss. Some systems are less efficient than 20% lost. So that's just kind of a generic thing. So some of this is the loss that I talked about in the unregulated video, which is about your connections and your wire resistance and all that stuff. And all these wires are a part of that too, just so you understand. But the regulator is your biggest offender. A very good buck regulator, for instance, could be 95% efficient, so you're only losing 5%. It could even be a little higher than that. But it's never 100% efficient. And you'll always lose at least a few percent. So if you had to make an assumption, 10% throughout the system is a very safe assumption to make, even though in a lot of cases it'll probably be less. So let's do our equation. We have watts out plus watts lost equals watts in. Now all your watts are accounted for, and they always have to be. By watts lost, it's not that they go out into infinity. It's that they're lost in heat throughout the system. Now let's go on to look at specific regulator types. Buck regulator, as we said before, is a step down. In this case, we have 8.4 volts going in, and we have less than 8.4 volts coming out. And just for this purpose, we have a 4 ohm or a 0.4 ohm atomizer. So I said it's less than 8.4 volts, but exactly how much less? Well, let's see. We have some things that affect the output of our buck regulator. The input voltage is the biggest one. And some people might not realize this, but when you load a battery, the voltage goes down. Let's say you have your regulator set to 7 volts. And if your battery sag below 7 volts, your regulator is not going to be able to put out 7 volts anymore. It will only be able to put out less than 7 volts. And the internal reference, which is a very technical term, at least for the purposes of this video, but essentially the regulator has to look at some set voltage and say, this is my reference point. Everything else is based off of this. A lot of regulators use 0.59 volts. And in that case, no matter what your input is, your output is never going to be any more than input minus 0.59 volts. You also have voltage adjustment setting limits. And all that means is the manufacturer, either by hardware or software, said you can't go any higher or any lower than these values. And for a lot of industrial regulators used in mods, that value is at 6 volts. However, that's a hardware setting that you can overcome by using different hardware components. However, something like a DNA 30, DNA 40, SX350, DNA 200, all of those are software limited. The only way you're going to change that value is by changing the software. And then you have output current level. Ultimately, the ability for a regulator to regulate depends on how hard it's taxed. If you're pushing a regulator very close to its current limit, there's a possibility, in fact a likelihood, that it's not going to regulate as well, so your output voltage won't be as hot. And that's something you simply have to deal with. So let's take our buck regulator, clean up the screen a little bit, and let's look at some basic truths about a buck regulator. So your higher voltage and lower current is going to be on the battery side of things. Your lower voltage and higher current are going to be on the atomizer side of things. So whenever your watts are all accounted for, and you lower the voltage at one point, you have to raise the current at that point. And I'll show you that. So we have an atomizer resistance of 0.4 ohms, a battery voltage of 8 volts. Our regulator is set to 6 volts. So our current, using Ohm's law, I equals V over R, is 6 volts divided by 0.4 ohms, which gives us 15 amps. And that's the current that's going to the atomizer. And that's power output of 90 watts. But that's not the current that's being drawn by the battery, or drawn at the battery, rather. So we take our output power of 90 watts, and we're going to assume a 10% loss throughout the system. And that's just an assumption based on what we talked about before with regulator efficiency and line losses. So we'll say 99 watts are being demanded of the batteries. If you have a battery voltage of 8 volts, the current, using Ohm's law, which is I equals P over V, 99 watts divided by 8 volts is 12.4 amps. Ultimately, that's what's being demanded by the batteries, or at the batteries. And you'll see the difference once we get into the boost regulator, why that's important. So one of the biggest safety aspects that we talk about with mods is battery safety. And the more current you demand of a battery, ultimately, the less safe your situation is. And that's a very broad general statement. That doesn't mean that you are in any danger by taxing your battery to its limits. But it is technically less safe in the sense that the more stress you put on your batteries, the more likely there is a failure. If we can stress the batteries less, then we have an inherently safer situation. And that's what we see with a buck regulator. Is we're demanding 15 amps, we're requiring 15 amps to get what we want, but we only need 12.4 amps from the batteries to do it. And I know that doesn't seem like a lot, but you're going to see how big a difference it makes when we get into a boost regulator. And we'll start that now. So a boost regulator, also known as a step-up, takes some kind of voltage. Here we're going to say 4.2 volts, so that's a single cell or parallel cells. And we're taking it and putting out more than 4.2 volts. Same thing as before, we have an output adjustment and we have a fire switch. But we also have voltage output limitations. And these are largely the same. Our input voltage, ultimately, as our battery sags, our booster may not be able to keep up with it, and that's important. The internal reference, once again, if we have, let's say, a 0.5 volt reference, then we can only put out 4.2 plus 0.5 volts, which would be 4.7 volts is then now the minimum output for this booster. So you can't get any less than that unless your battery sags. Same thing with the voltage adjustment limit settings. Those can either be hardware programmed or software programmed. The hardware being one that you can generally overcome. Then the output current level. Boost regulators are much more sensitive to output current level than buck regulators. Sometimes if you hear a whine coming from your regulator or from your mod, there's a chance that it's a boost regulator that's being overtaxed. It could be a number of other things, but that's one relevant thing that it could be for the purposes of this video. And when that happens, it essentially starts breaking down as a booster, and it defaults to providing battery voltage, whatever that is, to your atomizer. So regardless of what you have anything set at, unless you have a voltmeter attached to this, you may not be even getting the value that you think you're getting. And we're going to talk about that in a minute. But when you try to demand too much current of a booster, it simply stops being a booster and starts acting more like a fairly inefficient, unregulated mod. So be careful with that. So let's clear it out, and let's do a couple of basic truths. We have lower voltage and higher current being drawn from the battery, and we have higher voltage and lower current at the atomizer. Let's take the same situation. That should be 0.4, by the way. So we have a 0.4 ohm atomizer, the battery voltage of 4 volts, regulator voltage of 6 volts. Notice we're setting our regulator to the same point that we set it at for our buck regulator. And our current being drawn is going to be the same. 6 volts divided by 0.4 ohms is 15 amps. And our power demanded at the atomizer, again, is the same, 90 watts. So let's take that to the output. We're going to assume a 10% efficiency once again. So we have 99 watts demanded of the batteries. Battery voltage loaded for this is 4 volts. The current being demanded by the batteries is now 99 watts divided by 4 volts, which is 24.8 amps. Now that's a significant difference from the 12.4 amps that we were drawing before. And for all the reasons that I covered in the unregulated video, being efficiency issues that come from higher currents and lower voltages, that's one of the main reasons that boosters can find themselves at a disadvantage. Also, if you're trying to run this off of one cell that's rated at 20 amps, you're now going over the continuous amp rating, which is generally not recommended. By all means, you can do it. You're not going to hurt my feelings. But it's something you have to consider if you want to have the safest vaping experience possible. So the only other thing I wanted to talk about today regarding regulated mods is the fact that screens do not always tell you the truth. By and large, when you have a mod with a screen, and what I mean by a screen is not a simple voltage display that is wired into the system, because you see that in a lot of DIY mods. Someone will buy a voltmeter unit and wire it into the device, and it will display the voltage in real time. But that's not what I'm talking about. I'm talking about things like the more popular examples are the DNA40, the DNA200, the SX350, and so on. However, those screens, those companies have made their devices to where they only operate within limits that allow their screens to be accurate. When we talk about cheaper mods, especially, and I'm going to kick it old school for a second, the VAMO, and pretty much everything that came out around that time, around the 2011-2012 timeframe, this 6 volt, 15 watt paradigm for mods. And the Anakin, iTaste MVP, and basically all the Anakin devices that had screens around that time are in the same boat. And now newer mods, such as some of the Sigelis, are ultimately doing the same thing. And what that is the screens are displaying settings. Some of the values might be measured, but most of the primary values, and it depends on the mod, are settings. Let me show you this. So we're going to take the VAMO, because that one's near and dear to my heart. That was brand new around the time that I really started getting into modding. Lies! Well, sometimes. So this, we're saying it's set to 6 volts. And the question at hand is, does that mean it's always putting out 6 volts? And the answer is no, and I'm going to show you why. Let's look at the VAMO specs. So 3 volts to 6 volts that it can output. It has a 3 amp maximum current output. And as a note on that, you'll see some specs, some places say 5 amps. I assure you, they are not capable of 5 amps. Now, that is a pulse rating, and it does not reflect the continuous output of it. 3 amps is the best you're going to get out of a Vamo. And a 1.2 ohm minimum coil resistance. So let's go with that. Let's go with 1.2 ohms. So we're going to crank it all the way up to 6 volts. We're going to put 1.2 ohms on it. Current demand, voltage over resistance. 6 volts divided by 1.2 ohms is 5 amps. Wait a minute. This thing is software programmed to limit that output to 3 amps. It will not allow you to go above that. So how does it change what you do? Well, it does this by reducing the voltage below the screen value. And it does not indicate to you whatsoever that it's doing this. So the actual voltage, using Ohm's law, current times resistance, 3 amps times 1.2 ohms, 3.6 volts. So your screen says 6 volts, and it puts out 3.6 volts. So this is not just unique to the Vamo. There are quite a few boards out here that do this, and it's not something unique to old mods either. There are quite a few brand new mods on the market that do this. If you look at any of your Chinese companies, like Smoketek, Innokin, and Sigeli, they all have mods out there that do this. Unless they're using an SX series or DNA series board, it's probably going to happen. And even the SX and DNA series, they do their very best to be accurate, but some of those things displayed on the screen are still just settings. And you have to know the difference. You have to be able, and it's not that hard to see the difference. Ultimately, if the value changes when you do something like fire the mod or the battery drains or something like that, chances are it is a measured value. However, if it only changes when you click an up or down button, then it's a setting. And that should be pretty obvious for all of you. And if you want to see more of this, you can go to Phil Basardo's YouTube page, P. Basardo, and watch any of his regulated video reviews. And he shows this. He shows graphs of the limitations of these mods. Be careful with that. Don't assume that you crank something all the way up and put anything on it, and it's going to be putting out whatever you happen to calculate. As always, questions, comments, concerns, leave them below. This is just something I whipped up. If you want to see more, if you want to see me explain something more, just let me know, and I'd be happy to do it.